Jr. from Universidade Federal do Ceará, who will speak about the rigidity of compact quasi-Einstein manifolds with boundary. Okay, thank you, Ernani.
Thank you so much. First, I'd like to thank the organizer of the seminar for the kind invitation. It's a pleasure for me speaking here in this web seminar. Especially Juliette, Adrian, Henrique. It's very nice to see you, at least by screen. So today I'm going to talk about the rigidity of compact quasi-Einstein manifold with boundary. This is a very recent paper that I posted in the archive a couple weeks ago. This is a joint work with the Zhou and from Federal University of Niterói, Federal Fluminense University, and Jonathan Costa from UFC. So this is my plan of this talk. I'd like to talk about what is quasi-Einstein manifolds, what is the motivation to consider this kind of manifolds. Next, I will discuss some examples and open problems. And finally, I will show some rigidity results, okay? So let me start with the definition of quasi-Einstein manifolds. This definition is back to 70s, but with this configuration here is already known by in the best books. It's a classical book about Einstein manifolds published in the middle of 80s. So, but in this configuration precisely can be seen in this paper of 2011 by Zhou anyway. So the quasi-Einstein manifold is essentially a Riemannian manifold together with a potential function f satisfying this equation 1, or here is the heat Fm is the Ricci plus Hessian of this potential function minus 1 divided by m, and then this tensorial product between the one form associated to this potential function f. So, and then becomes proportional to the metric. Lambda and m here are constants, okay? So, and this term here, heat Fm, is also known in the literature as a Becker-Emery-Ricci tensor. It's a modification of the Ricci tensor, okay? So this terminology comes from the study of the diffusion operator by Becker and Emery by using this modified Ricci curvature, okay? And this tensorial product is essentially what I did, what I put here in the last line, okay? It's a symmetric property. So this is the definition of quasi-Einstein manifold, but why we consider this kind of manifold? We can see this kind of manifolds and this problem as an overdetermined problem, because you are looking for potential function f satisfying this equation for some for a given Riemannian manifold. Okay, so but among the motivations to consider this kind of manifolds, we have many motivations. I have here a list. Okay, they are connected to the study of Einstein manifold. They are connected to gradient Ricci solitons, static space, and Einstein work product, and also smooth math measure space. I will give a very brief idea of each motivation and in the next slide. So, for example, when the potential function f here is constant, the equation becomes the Einstein equation. In other words, if f is constant, we obtain the Ricci is proportional to the metric. In certain sense, what I'm saying that any Einstein manifold is a trivial example of quasi-Einstein manifold, but trivial in the sense that this potential function f is constant. However, here in this talk, we are interested in non-trivial examples. We are looking for potential function f non-constant satisfying this equation, okay? But we can see them as a extension of Einstein manifolds. And we know in geometry, there are many reasons to consider Einstein metrics as the best metric on a given manifold. So then we have this connection as well. So they are also connected to the theory of gradient-rich solitons. The theory of gradient-rich solid becomes very famous in the last 2 decades due to the solution of the Poincaré conjecture by Perman using the singularity models. Is precisely what appear when you consider gradient-rich solid. They represent singularity models of the rigid flow. Interestingly, is when you take when m goes to infinity, this last term in the equation becomes 0, and then we recover the richest soliton equation. Okay, so but let me mention here that despite of this similarity, there are some examples with stark contrasts to the richest soliton theory. And moreover, despite of the similarity, let me mention that the study of quasi-Einstein manifolds is older than richest solitons. The study of richest solitons starts around 82 in the classical paper by Hamilton, where he introduced the richest flow. And this notion of quasi-Einstein manifolds appear in physics paper that I will mention in a few minutes. So another motivation comes from the study of static space. When m is precisely 1, this equation of quasi-Einstein manifold becomes the static equation. F tilde is a little modification of the potential function. So in other words, a quasi-Einstein manifold with m equals to 1 is precisely a static space. Okay, and this static space, this terminology comes from the related problem in general relativity, which gives solutions to the Einstein field equation. Okay, so till now, I just mentioned generalizations or extensions, but in my point of view, the main motivation to consider this kind of manifolds is precisely this one here in this slide. So as I said a few minutes ago, Einstein manifolds can see as a best metric on a given manifold. There is this classical book about Einstein manifolds by Bess, and then this book gives many reasons to consider Einstein metrics as a best one. So, and one of the mention that that appear in this book, exactly in the page 267, is about the connection between quasi-Einstein manifold and the worker products. One question proposed by him in the book is how to construct new example of Einstein metrics on a given manifold. And the study of quasi-Einstein manifolds is one way to produce new example. It's exactly the content of this result here in the end of the slide. If you have a quasi-Einstein manifold, which means a Riemannian manifold together with a potential function satisfying this equation, then we have naturally a lambda Einstein work product metric. Then this gives us a natural way to produce new Einstein metrics on a manifold here in a work product. Okay, so this construction also appear in a new book about semi-Riemannian geometry, and in classical papers about about quasi-Einstein manifolds. Okay. So
sorry, Ernani. Perhaps I missed something. Who is the capital F there?
Sorry, capital F. Okay.
In the product.
I see. Okay. This is the following. I will just mention in a few minutes how is this F, because this F here is we can choose any fiber with a specific value of Einstein constant. F will be another Einstein constant, and this F here depends on the sign of one expression that I will mention in a few minutes. Okay. But
okay, thank you.
Let's just keep in mind in this moment that F is any fiber, okay? The dimension of this F should be exactly this M here, which appears in the equation, okay? This is why I consider M to be positive. But F cannot be N1. I will show in a few minutes why. But in certain sense, in this point, you can consider any fiber, but we will see that this fiber should be Einstein as well. But the Einstein constant will be different from this lambda here. What is Einstein here with lambda to be a constant, or the Einstein constant, will be this all product, okay? All product metric. So as I said, this motivation appear precisely in these two books. There's one, Einstein manifolds, in the page 267, and also some examples of this kind of manifolds. So
just real quick, what's a capital F? It's a circle bundle. It's a what's capital F?
Not necessarily. We can choose any manifold with one precise value of. Let me just show in the here.
Oh, I don't want to spoil it.
Yeah, it's necessary because you can choose any Einstein metric with Einstein constant to be exactly this value here, mu.
Fine, but so for the time being, capital F is just a manifold.
Yes, a Riemannian manifold, but should be an Einstein manifold as well.
Oh, so okay. you want F to be Einstein?
Yeah, with
the twist. Is that
it? Sorry, I didn't hear. Sorry.
Yeah, I just want to know. So what is F, right? So M is your original quasi-Einstein, and F is what?
F, you can exactly look at that. M is a quasi-Einstein, okay? Then we are able to produce a new manifold. Which manifold you can put here? We can choose any manifold to be F, but this manifold F should be another Einstein manifold with Einstein constant, precisely that mu that I mentioned in the filter. Okay, that I spoil you. Okay.
Okay, gotcha.
The point is, we are able to obtain a new Einstein metric when you do that. Okay.
Gotcha.
This is the point.
Gotcha. Thanks.
And F, we can change F if you want, and we obtain another metric. F can be changed, but should be another Einstein manifold with the same constant that I mentioned in another slide. Okay. So thank you. So there is another motivation very recently, maybe 3 or 4 years ago, in physics. Some mathematicians from the United States, some physics from Canada showed that quasi-Einstein manifold is also related to the horizon limit and in a black hole. But these are motivations in physics that I'm not too familiar yet. But many mathematicians and physics guys in the United States and Canada have been trying to classify them in the last 4 years, okay? So let me just mention that this term with the tensorial product sometimes is hard to deal with. So essentially, when M is finite, in other words, when such manifold is not a soliton, because when M goes to infinity, I obtain a reach soliton, or in this case, you can take this change of the potential function f. You can consider u to be the exponential of minus f over m. Then this quantity here in the equation just becomes this, and then we can see the fundamental equation like this. It's very common because depending of the author, some author consider quasi-Einstein manifolds with these equations. The another one consider the quasi-Einstein manifold with this equation here, okay? But they are equivalent when you are considered M to be finite, okay? So in this talk, we are interested in the case of compact with boundary. Then you consider the definition of quasi-Einstein manifolds considered by He, Peterson, Wiley, and other authors around 2010. Here, we have boundary, then we assume some boundary conditions, okay? So to them, a compact Riemann manifold will be a quasi-Einstein manifold will be a compact manifold with boundary satisfying this system too. And here we consider the potential function to be U, okay? So then the equation is this blue column, which is precisely the another one, okay? It's just organize the terms, put the right side, is the same equation, okay? And then we are also assume this boundary condition. U should be 0 on the boundary, okay? These boundary conditions will be very important for us because these boundary conditions will guarantee that the boundary is totally geodesic, okay? This is a very important information for us. So from now on, a quasi-Einstein manifold compact with a boundary will be a Riemann manifold, compact manifold, of course, satisfying this system too. Okay, it's equivalent to the other one. Okay. An interesting fact that I like to mention here is this theorem. This theorem by Hippitis and Wiley in the case of with boundary, and by Keon, Beckley, and Emery in the case without boundary. They show that if you have a quasi-Einstein manifold, and such manifold will be compact if only if this constant lambda is positive. In fact, who work in the rich solitons or Einstein manifolds will know that the sign of this constant has a great influence in the geometry of such manifolds. It's exactly what happened here when you consider quasi-Einstein manifolds. When lambda is positive, if only if such manifold is compact. But interesting is we can see quasi-Einstein manifolds as generalization of rich solitons. However, this is a stark contrast to the rich soliton. Observe, for example, this fact here. We know by Meyer's theorem, if the rich curvature is bounded from below by a constant positive, by Meyer's theorem, we know should be compact. A complete manifold should be compact. However, if you go to the rich soliton equation, if the rich plus Hessian F is bigger than or equals to lambda, lambda positive, this does not imply compactness. Why? Because we can get a counterexample to be the Euclidean space and the potential function to be 1/4 of the norm of the position vector square. Okay, so here we are looking for a non-trivial potential function f. So in that case, we know this is does not imply compact. However, this theorem by Hippitis and Wiley and Kian Becker shows that the Meyer's theorem still holds when you consider read Fn, when m is finite. And this is a compactness theorem, we can see like this. And observe that this change in the tensor, in this modified Ricci curvature, has a great influence in the geometry of this object. Okay, so then we are interested in the system here, system 2, and functions U satisfying this system. But here are in the geometry seminar, and we know we have afraid to work in an empty set. But how about examples? So in dimension 2 and 3, we already know all possible examples by Best's book. This classical book about Einstein manifold, we already know all possibilities. Then here today, I will mention some examples in dimensions bigger than equal to 3 at least. So, but let me start with the first example, okay? This first one example is the hemisphere, and this example is true for dimensions bigger than equals to 2, okay? This first example is the hemisphere, this is the metric, and the potential function is the cosine of the height function, okay? Observe that to get an example, I need a manifold, a metric, and a potential function. And of course, by this result by He, Peterson, Wiley, Becker, and Kian, we already know in the compact case, with boundary and without boundary, we know that this constant lambda must be positive, always, okay? So then we already know the sign of lambda. So the hemisphere is the first example. This example has connect boundary, okay? So this is a well-known example in the literature, okay? So this example is true for dimensions bigger than equal to 2, and this example is a quasi-Einstein, and at the same time is an Einstein example, okay? The Ricci curvature is constant, okay? The second example is the cylinder, which is the product of the interval cross a sphere, and this is the canonical metric, and the potential function depends only of this factor I here, okay? So another example. The second example has a disconnected boundary because the boundary has two components, okay? So the boundary will be two spheres, okay? And this example is not Einstein, okay? It's a quasi-Einstein, but not Einstein. The third example is a very recent example obtained by Diogenes Gadelha and myself in 2021, which is the product of the hemisphere times a sphere. This example has this metric here that I put here in the slide, and the potential function u depends of the height function in the hemisphere, okay? So this example also has connected boundary. The boundary of this example is the product of two spheres, okay? This example 1 is true for dimensions bigger than equal to 2. The example 2 is true for dimensions bigger than equal to 3. This example 3 obtained by myself is true for dimensions bigger than or equal to 4. Okay, this only appears in dimensions bigger than 2, 4. Any questions so far?
Yes, Ernani, one question. What are the values of the parameter m in these examples?
M here can be any value here in these examples.
For any value of m?
M can be any value here.
Okay, okay.
Yeah,
great.
In these three examples, there is no problem in M, okay?
Mm-hmm. Thank you.
Welcome. Including m equals to 1, if you want. We can consider static spaces. These examples are also static, okay? They are not soliton, okay? Because soliton, we don't have a soliton with boundary. This should be very clear. Here, m should be finite. So we have these three examples. We have these models. We can also produce another examples for dimension bigger than 2.5, just replacing here the sphere as n-1 or SQ by a lambda Einstein manifold. If you put any lambda Einstein manifold, for example, the product of two spheres here, we have another example, okay? The product of two spheres, we have another example. But if you are mentioned, for example, dimension 3 and 4, by the Killing-Hop theorem, we only have these three options. We don't know another examples, okay? So let me mention one important remark. As I said, this first example has a constant Ricci curvature, okay? It's the only one which has constant Ricci curvature. But interesting is these three examples, they have constant scalar curvature, okay? They have constant scalar curvature. So, okay. So this example 3 obtained by myself and Diogenes Gadelha has also a special interest in static space, okay? That is a famous conjecture proposed by Bolshoi, Gibbons, Yorovich, the Cosmo-Hecke conjecture. And this example 3 also provides a counterexample to the Cosmo-Hecke conjecture. The Cosmo-Hecke conjecture is the following, is the hemisphere is the only possible simplified connected positive static space with connected boundary and positive scalar curvature. And here we have a counterexample for dimensions bigger than equals to 4. We already know a counterexample by by Gibbons and Pope in 2003. However, the counterexamples are only for dimensions between 4 and 8, and the counterexample are not simply connected, and moreover, the counterexample are not explicitly like us, because here I show explicitly which one is the manifold, the metric, which one is the potential function. Okay, so okay. So, but how about the uniqueness of this example? We know these 3 examples are the only known in dimension 3 and 4 and 2, but how about the uniqueness? As I said, the first one is the only one Einstein. So this motivates he, Peters, and Weil prove this theorem. He proved that if I have a compact quasi-Einstein manifold with boundary, and then such manifold has constant rigid curvature, if only if it is isometric in the first example. Okay? So then you have the uniqueness under this constant rigid curvature assumption here. However, the 3 examples that I mentioned, the hemisphere, the cylinder, the product of the hemisphere times the product with the hemisphere with the sphere, they have constant scalar curvature. And then this motivate these questions, which is still open at least 10 years, about the uniqueness of the quasi-Einstein manifolds compact with boundary and constant scalar curvature. Okay, so this is the main question of this talk. We are interested in this problem, okay? And in dimension 2, we already know a classification. It follows by Rayleigh theorems, the classical Rayleigh's formula, or by best books, or we can use the result by Peterson and Peterson Weil. So in dimension 2, we know that if I have a 2-dimensional compact quasi-Einstein manifold with a boundary, and here I have one important information. M should be bigger than 1. In other words, I'm saying that cannot be a static space, because the static space, which is precisely the case M equals to 1, should be done in a different way. But excluding this case, if you put away the case of M equals to 1, we know that a 2-dimensional quasi-Einstein manifold with a boundary has constant scalar curvature if only if is the hemisphere. Exactly what we expect, because it's the only one knowing example in dimension 2. Okay? But how about dimension 3, 4, or higher? So in dimension 3 is exactly the content of my theorem A. Okay? We prove that if I have a non-trivial simply connected 3-dimensional quasi-Einstein manifold with boundary, and here I put away the case M equals to 1, the static space. Okay? So then M3 has constant scalar curvature if only if it's isometric to the hemisphere or the cylinder. Precisely what you expect, because the 3rd example is only true for dimensions bigger than equals to 4. Okay? It's clear. Any questions so far? Okay, so then we are able to solve the problem in dimension 3. Okay, so but how about dimension 4? Let me mention here the case of dimension 3 is not too hard. Okay, the case of dimension 4 call more attention for us and becomes much more intriguing. Okay, we know that dimension 4 has special behavior, display a fascinating peculiar features. And in large part, This is because the bud of two forms can be invariantly decomposed as direct sum. So I have special interest in dimension 4, and dimension 4 have special interest in general in geometry. Okay, so but what can you say about dimension 4? What we expect? Okay, when you're looking for this example, we expect to prove that under the constant scalar curvature assumption should be example 1, 2, or 3, because the example 3 already holds in dimension 4. So it is exactly the content of our theorem B. Our theorem B says that I have a non-trivial 4-dimensional quasi-Einstein manifold with boundary. And here, again, I put away the case m bigger than the case m goes to 1. Then we are able to show that it has constant scalar curvature if and only if is a hemisphere or a cylinder or the product of the hemisphere times the sphere. Exactly what we expect. Okay? So then we solve the problem in dimension 3 and 4. However, the problem is still open for higher dimension. We are able to prove in dimension 2, in dimension 3, and dimension 4. Okay? But how can we prove this results? So our strategy is inspiring some recent results which classify gradient-rich soliton with constant scalar curvature. As I said, that there is no boundary in the gradient-rich soliton. Then we need to deal with this obstacle in our strategy. Okay, so but let me try to give. Of course, I will not show the details how can prove this, because this is a big paper with 40 pages. But I'm trying to give just a general idea how we can do that. Okay. So we start with this lemma. I know that's a lot of formulas, a lot of terms. Okay, but but I will try to explain why this is interesting. I know this is ugly, but it's interesting. Okay, just to begin, Enrique and Adrian asking me what is f in that Wolper product. F should be exactly the constant here, mu, which appear. F should be an Einstein manifold with Einstein constant mu to be this value which appear when you complete this term. Okay, and then F cannot be any manifold. Should be an Einstein manifold with this mu to be the Einstein constant. Okay, so let's back to the case of constant scalar curvature. Here we are interested in the case of constant scalar curvature. So this form was proved by Case, Zhou, and Wade, Hippett, and so on. When you consider constant scalar curvature, observe that in this first equation, this term here disappears because are some constant scalar curvature. And then, in certain sense, what is this equation implies that the gradient of the potential function is an eigenvector of the Ricci curvature. But of course, this term cannot be zero. This is one of the reasons that we put away the case m equals to 1. Okay? Of course, we need to put this restriction in several times, because the case m equals to 1 becomes static, and then the approach should be different. But this is one of the places that we need to consider m different of 1. Okay? So, but the first information that comes from this equation is in the constant scalar curvature case, the Ricci curvature becomes the gradient of u becomes an eigenvector of the Ricci curvature. Another information interesting in this equation C is that in the case of constant scalar curvature, this term in the left-hand side disappear. This first one in the right-hand side, also disappear. And then this quantity, which gives the trustless rich tensor only depends of this value here in the last line, which is constant when you consider R to be constant. In other words, when you have a constant scalar curvature in a M quasi-Einstein manifold, in general, this is true in general, not necessarily compact with boundary, or in general, non-compact and compact, we can say that in the case of constant scalar curvature, the gradient of potential function becomes an eigenvector of the rich curvature, and with associated eigenvalue to be n-1 lambda minus r divided by n-1. And moreover, we are able to show the gradient of u, it's a function here which only depends of u. In other words, u is a transnormal function, okay? And also, just taking a trace of the fundamental equation, we show that the Laplacian of the potential function is a function which only depends of u as well. In other words, u is as an isoperimetrical function, okay? This theory of transnormal and isoperimetrical functions will be very useful for us to prove our first theorem in direction to prove this, the theorem A and theorem B, okay? So with this approach of transnormal and isoperimetrical function, we are able to prove this first theorem, okay? The first theorem says that if you have a non-trivial compact M quasi-Einstein manifold with boundary, non-trivial for us is that the case of the potential function is not constant, and remove the case M equals to 1, under this constant scalar curvature condition, we know precisely which values the scalar curvature can be, okay? Here, we have the list of the possible values for the constant scalar curvature, okay? In particular, I have a formula here which depends of the value of k, which runs from 0 to n-1. We have a list, a precise list of values to be constant scalar curvature. With this list, we can do some argument. For example, we know we are looking for constant scalar curvature condition. Then if the first value here holds, if the lower boundary, this lower value in the list holds, what we have? Back to the equation C here, we know in the case of constant scalar curvature, this term disappears, there's another one disappear. The first one, the right-hand side. The Hess terms is precisely this formula here, okay? So then, if you have a quasi-Einstein manifold with constant scalar curvature and m bigger than 1, then you have this equality here. So, but if you assume that the scalar curvature is the first possible value, this lower value here, observe is precisely this term b0. But if this term is 0, then the rich curvature becomes proportional to the metric, and in other words, the manifold becomes Einstein. Then it's sufficient to use by Petersen-Wiley theorem to conclude that such quasi-Einstein manifold must be isometric to the hemisphere. In other words, when you're looking for the list, the first possibility for the value of the constant scalar curvature should be the hemisphere. The first one here should be the hemisphere. Okay? Any questions so far? Now, let me looking for, sorry, any question? No? Okay. Now, if you're looking for the upper value here, okay, n-1 lambda. In this case, we are able to prove this theorem too. In the case of the upper value, observe that example this theorem 1 and theorem 2, they hold, and for any dimension bigger than equal to 3. Okay, all theorem A and B are specific to dimension 3 and 4. Okay, but this time we have results for any dimension in this point. Okay, when you consider the upper value, we are able to show that a quasi-Einstein manifold with a boundary with constant scalar curvature precise this upper value should be isometric to the cylinder E cross N, where N is a lambda Einstein manifold. In dimension 2 and 3, this N, by using the Killing-Hopf theorem, should be exactly the sphere, should be a cylinder. Okay? So then we solve the first case, should be the hemisphere, and the last case here should be the cylinder. Okay? However, we have middle terms in this list. Okay, let's now look for the proof of theorem A. Remember, in the theorem A, we have this classification. If you have a constant scalar curvature in dimension 3, then a compact quasi-Einstein manifold has constant scalar curvature if only if it's isometric to the hemisphere or the cylinder. Okay? So, since you are assuming constant scalar curvature, we may use our theorem 1 to get a list of possible values to be this constant scalar curvature. This possible value should be 6 divided by m plus 2 lambda, or m plus 3 divided by m plus 1 lambda, or 2 lambda. However, we know that the first one here should be the hemisphere. The last one should be the cylinder. What you do is precisely to show that this middle term does not hold. Okay? Then this proves theorem A. Okay? How about the theorem B? Let me back to theorem B just to recover just to recall the statement. So the theorem B, you have this similar classification result, but here include the product of the hemisphere times the sphere. Okay? So again, by assuming constant scalar curvature, assume constant scalar curvature and m bigger than 1, we have 4 possibility now. Okay? The scalar curvature should be one of this value. However, we already know that the first one is the lower boundary value and should be the hemisphere. And the last one, the upper value case, should be the cylinder. Okay? What we have is precisely this. The first one should be the hemisphere by repeat and so wide. The last one should be the cylinder by our theorem 2. The second one, we are able to show that does not hold. It's just a topological argument, it's not hard, it's very simple. And the problem is this third one. And interesting is, this third one is exactly example 3. When you compute the scalar curvature of example 3, we show that example 3 has this constant scalar curvature. Example 3 is the product of the hemisphere times the sphere. And this fact has left open the questions about the uniqueness of this example under this precise value of the constant scalar curvature. Okay? So, and this uniqueness question is answered by our theorem 3. In this theorem 3, we prove that if you have a compact quasi-Einstein manifold with boundary and m bigger than 1, if the scalar curvature is precisely this value, if only if is the product of the hemisphere times the sphere. Observe that differently of theorem 1 and theorem 2, here the result is specifically to dimension 4. Okay? And then with this answer to this uniqueness question, when we back to the theorem B, we finish the proof, because the first case will be the hemisphere, the second one does not hold, the third one should be the product of the hemisphere times the sphere, and the last one should be the cylinder. Okay? As I said, this theorem, which is crucial in the paper, is true, holds just for dimension 4. It's specific to dimension 4, but it's incredible because around 70 or 60% of the paper is devoted to prove this theorem. This is I can say that this is the hard part of the paper. Okay? And then, how can prove this hard part of the paper? Around 60 or 70% of the paper is devoted to this theorem 3. So the idea to prove the theorem 3 is not too hard to understand. But let me just mention how you prove that this uniqueness in the case of the product of the hemisphere times the sphere. So we start with computing the Laplacian of the Ricci curvature. When you have R with 2 indices, the Laplacian of the Ricci curvature. Okay, this is the initial formula. Okay, here we do some tensorial computations. Okay, with this, we observe that it's much more convenient to work with this another tensor P. This tensor P is a modification of the Ricci by this term Rho G, where Rho is precisely this value. With this modification of P, if you back here, this Rho is precisely the value which gives us gradient of U to be the eigenvector. In other words, this implies this tensor P, we give us the information that the gradient U is an eigenvector of the tensor P with 0 associate eigenvalue. Why this is interesting? If you look at now for the tensor P as a matrix and take if you diagonalize this matrix, we have 4 possibilities to the eigenvalues. Okay. However, the first one will be 0. Okay. This will be very important information. And then we already know 2 formulas. We know the trace of this tensor P is this quantity here, because the first eigenvalue is 0. And you know the norm of P squared is this quantity which also depends on the trace of P, and the trace of P is a constant. In other words, we have 3 unknowns, because the first one here is 0, and I have me2, me3, me4 unknowns, and I have 2 equations. And then the problem becomes a problem of linear algebra. I need a 3rd equation to solve the problem. Okay? But how get the 3rd equation? Our strategy is to compute the Laplacian of the trace of P power 3. P power 3 is this multiplication of P 3 times here with the trace in these indices here. Okay? For us, we assume the Einstein conventions and sum of repeated indices here. Okay? When you compute this, which is not too, it's hard to compute, we get this formula. It's a very tricky formula. Okay? But with this formula, we are able to get the 3rd equation, because after several computations, we are able to get this information here, which will be in our 3rd equation. Of course, just with these equations, it's not too simple to solve the problem and then say which values will be the eigenvalues of P, but you do some analytical arguments, and using this this elliptic operator here, and then we get this inequality, and then in this specific value of the constant scalar curvature, we have this inequality, and by using maximal principle argument, we are able to obtain this this equation here. The trace of P3 minus 2m power 3 whole 3 is 0. And then when you back to these equations, the red color, this term on the right-hand side becomes 0, and then the product of these eigenvalues will be 0. And the metric of a quasi-Einstein metric is analytical, and then at least one of this eigenvalue will be 0. And then we are able to solve the system and obtain all values of the eigenvalues of the tensor P. And then we back to the tensor, the Ricci tensor, and then we are able to construct our isometry. Okay, so this is of course a general idea. Okay, of course I'm not sure the details, but this is one of the idea to get the result. So thank you so much. Thank you.
Yeah. Okay. Thank you very much, Ernani, for this very nice presentation. And so, do we have questions from the audience? Yes, Nelia, Marcia, if you want to ask something. Yes, Nelia?
Hi.
I don't know if it's correctly pronounced. Hi.
Thanks, Ernani, for the lecture. So I understand why you consider the case m greater than 1, but I think I don't understand the situation for the case m equal 1. I want to know if there is a result like this proved for this case.
I see. Okay, very nice question. So the case m equals to 1, this is much more intriguing for us, and there is some conjecture related to this, the case m equals to 1. There's the Fisher-Massey conjecture, there's the Cosmo-Hare conjecture, which is always I show a counterexample the Cosmo-Hare conjecture in dimensions bigger than equal to 4, but this conjecture is expected to be true in dimension 3, then it's still open in dimension 3. And there is also the Fisher-Massey conjecture for static space associated to this kind of problems of rigidity results. So in the case m equals to 1, the problem is, let me give
this part I understand why
I explain.
Yeah, this part I understand why m is greater than 1. Only the case m equal 1, I want to know if this theorems is open problems for the case m equal 1.
Yeah, in the case m equals to 1 is an open problem. Let me say why. When you're looking for this theorem, this value k here, it's very intriguing because this k here is precisely the dimension of the maximal, the set of the maximal values of the potential function. If you consider the set of the points in M such that U computing this point is the maximum value, the set of the maximum value of U, the dimension of the set is precisely this value k here. Let me explain, for example, in the case of the hemisphere. We have the hemisphere, the maximum value of the potential function is the North Pole, just the North Pole. Then the dimension is 0. In this case, equals to 0 because the dimension of this maximal point. K equals to 0 is precisely this first value here. Remember that I showed that should be the hemisphere.
Mm-hmm.
In the upper value here is precisely k equals to n minus 1. It's exactly the cylinder. If you have the cylinder, the maximum is obtained in the neck. This neck is a submanifold of dimension n minus 1. Exactly this value of k. in other words, it's interesting and it's crucial to prove this set of maximal points of U has some differentiability, is a smooth manifold, because we need to compute, we need to do some argument in this case. In the case of static, in the case m equals to 1, we are not able to show this maximal, the set of maximal point of U is a manifold, is a smooth manifold. This is a key step.
Understand.
And the problem is still open in the case m equals to 1.
Thanks for the answer.
Thanks for the question.
Okay. Is there any other question for Ernani? I do have one.
Okay.
You say that you have a finite number of possibilities for the scalar curvature, depending on k.
Yeah. Yeah.
And in dimension 4, you said that one of these values could be easily erased.
Yeah, in dimension 4 should be the
second one.
Should be, yeah, the second one cannot hold. Yeah.
Yeah. What happens in higher dimensions? Are there some values that you can easily erase, like this one?
For example, if you're looking for higher dimension, yes, we are able to show that the second one does not hold any time.
Okay.
Okay, the second one, because in the second one we do some topological argument to show that the dimension of this maximal value of the potential function is 1. In this case, this case of dimension 1 cannot hold, and then this does not depend of the dimension of the manifold. Depends of the dimension of this maximal, the set of maximal points. Okay, if you go for high dimensions like 5, 6, 7, the problem is something like a linear algebra problem, because we have just 2 equations. Then we do the computation to looking for the p power 3 to get another equation. And then if you go for dimension 5, for example, the idea is we need another equation. And maybe we need to compute the power of 4. Okay. And if you go to dimension 6, maybe I need to compute one more equation, the power 5. And so there's one of the reasons that I put this formula here, just to show you the power 3, it's hard because a lot of terms. If you go for power 4, we have more terms. And then we believe there's some cyclical arguments to overcome this difficulty here, but we don't know yet how to do that.
Okay, so far you can only erase the second value for any dimension.
For any dimension, the second value, because in the second value, the dimension of this maximal point of U is go to 1, then we are able to use some topological argument and remove this case for any dimension.
Okay, well, thanks. Okay, is there any other question for Ernani? Well, if this is not the case, well, let's thank Ernani again.
Thank you.
Thank you for this very nice presentation again.
Thank you so much.
There is
one raised their hand.
Another question by Chantal? No. Okay. Then we wait for all of you again in 2 weeks' time, when we have another session of this webinar.
Just real quick. So people find in the chat the instructions to join our mailing list, our announcements WhatsApp group, as well as check previously recorded talks on our YouTube channel, and to subscribe to our Google Agenda. So please have a look at the chat, join the WhatsApp group, check our calendar, the rest of it, right? These are ways to stay in touch with us. We have talks every 2 weeks. Just because there are several new people today, so.
Okay.
Just making that, including yourself, Ernani. Please join the list and stay tuned.
It'll be a pleasure. Thank you, Henrique. Thank you so much.
Yeah.
Okay.
Bye.
Bye
Okay,
bye.
see
Bye
you
bye. Thank
then.
you,
Bye
Adrian.
bye.
Thank you, Juliette. It was a very pleasure.
Ciao,
Thank
ciao.
you. See you next week. Bye bye.
Yeah.